Welcome to Physics Lab 1, the amount of excess charge on an ordinary object. The purpose of this lab is to observe the transfer of electrons using tape, and then to use the data collected to calculate the charge on said tape. As for the results, the charged tapes repelled each other, with the charge of the tape being 1.5 e to the negative 8 coulombs, and the tape being deficient of 7.206 e to the 10th electrons. This lab uses Newton's second law to verify that the forces are equal in magnitude. We also use Coulomb's law to actually calculate them. Models and assumptions. First, we have to consider each piece of tape as a point charge and describe the electric forces caused by the repulsion and the force of gravity of Q1. We must assume that there is no air drag and that the charge in the system is not lost to the surroundings via user handling, which is likely not true. The experiment setup is as follows. The system is the tape on the table as well as the ripped tape. Our initial conditions via measuring tape were that the length of the tape was 8 inches or 0.2032 meters. The width of the tape was roughly 3/4 of an inch, which I also converted to meters. And then the mass of the tape was just the length of the tape divided by 1,000. The distance between the tape, of course, was 0.0245 meters. As for our observations, the ripped tape was ripped off of the table tape, and the ripped tape attracted my hand, just like the figure shown. Whenever we rubbed the pencil against the cloth, it gained a negative charge, and from what we observed, it attracted the ripped tape. Thus, the ripped tape is positively charged. Ripped tape A also repelled ripped tape B, meaning that whenever we repeated the experiment twice, the result was the same both ways, because the only way that they could repel each other is if they were of like charge. And then here's a free body diagram of what we put together. That image on the left is whenever we tested the two ripped tapes to see if they repelled each other, and they did. Then the right shows the distance d, the separation distance between the two tapes. The system, of course, is tape B, and the surroundings is considered to be tape A, because it's externally applied to tape B in this scenario. On the left, you can see my glow script code. At the top, I declared all my constants. PHYS is Coulomb's constant, the length of the tape, the width of the tape, the mass of the tape. This was all measured beforehand. Variable g is, of course, the acceleration due to gravity, and the scale factor is applied to the visual model that we generate so that it's easier to see, given that we're working with very small particles. As for the math section, first you calculate mg, and then you take the absolute value of that to get the electric field force. Next, you calculate the charge of tape 1, and then we find the number of electrons by dividing the charge of tape 1 by the charge of an electron. From there, you find the number of atoms by finding the area of the piece of tape, and then dividing it by the length of an atom squared. From there, you can also find the amount of atoms for every electron on the piece of tape by dividing the number of atoms by the number of electrons. In the object section, I just declared the tape 1 and tape 2 as objects, and then plotted the electric field force and the force due to gravity. You can see it on the model to the right. One thing to note about that model is that the magnitude of the two arrows is the exact same, which reflects what we know about Newton's second law. It's pretty cool. As for possible sources of error, handling the tape likely caused a loss of charge, and reducing the tapes to point charges is risky. You see, these are complex objects, and the loss of charge is going to happen whenever you touch the tape with your hands. It's going to cause the tapes to return to stability. Noted similarities, however, are that Newton's second law was present both in our model and in our calculations. What if the charges were switched? What would happen? Well, nothing changes. The electrons present before and after would still exist. You're just switching where they are. And thus, the tape would still repel the other tape because they would both still have the same charge, and they would still be attracted to the pen. Because in this scenario, the pen also has switched charges, and thus the relationships are still the same. It's important to handle the charged tapes as little as possible, because touching them can cause the tapes to return to stability via their electrons. The electrons on your hands move back onto the tape whenever you touch them. That's why it's important to handle them only at their ends. Let's use the 30-second grace period after the 5-minute mark to discuss the conclusion. Everything is physics. Everything that you touch can be considered an interaction between two pieces of matter. Additionally, you can use simple checks like the pen on the tape to verify if the tape has a positive or a negative charge. I just find it really cool that you can reduce something as complicated as that, figuring out what kind of charge it has, to just a simple check. Thanks for watching.